Hey guys, this is Ms. Morrison, Sarah, and we are going over logarithmic functions. And in Blackboard, there should be some old college algebra notes under the handouts that say logarithmic functions. They look like this. The paper is side to side. And I think it says 4.2, but that's because it's for college algebra chapter. But it's all the same math, so we're going to be looking at this. Okay, the best way I can explain logarithmic functions is it's an easier way for us to write numbers. Really, really big numbers and really, really small numbers. Like, let's think about, let's say I'm here on Earth and I want to travel all the way to Mars. Okay, that's a long way away. I don't know how much way away it is, but let's just pretend. Let's pretend it's like, I don't know if this is true, just pretend, okay? Let's say it's this many miles away. Mars is this many miles away. Well, if I'm this astronaut, I have to not only know the software of the rocket ship and how to deal with the software, but I also have to know how to do the math myself in case the software or the rocket ship dies and you have to do the math yourself. You've seen that on a movie. Okay, well, if we're that little astronaut floating around in the sky, we don't want to be doing the math with this number. This is a huge number. Chances are we're going to do something wrong. We're going to write it down wrong. We're going to look at it wrong. And, you know, if I'm trying to go to Mars and I get my math wrong, I might end up in the sun. So, for really, really big numbers or really, really small numbers, we use something called exponentials. So this 10 is actually called, this 10, whatever this is, bagillion, whatever. It's actually called 10 to the 3, 6, 9, 12. 10 to the 12th. Yeah. So as an astronaut or a mathematician, we can use exponentials to describe very large numbers or very small numbers. The problem is when we start doing math with these kind of numbers, it gets icky. And that's where logarithms come in. So you might not have ever seen a logarithm, but it's because when we get up into that high math of rocket ships and bacteria and vaccines and all that super fancy sciencey stuff, the freakishly big numbers become very difficult to work with because they have a base and an exponent. And we can use logarithms to kind of rearrange it and make the math way easier so that we're not writing 12 zeros every 5 seconds. Okay, so the point of logarithmics is to be able to do math with exponentials. And exponentials are for really big or really small numbers. Okay, so first it says convert. That just means switch. It doesn't mean find the answer. It doesn't mean find the amount of years or the amount of bacteria or whatever. It just means switch the stuff around. Yeah. Okay. So let's say I have this sucker, b to the y equals x. And that's actually right what we're looking at right here. I kind of simplify it a little bit more in my college algebra handouts. And I say that b to the y equals x. I don't like the x and y. It kind of gets me. But anyway, I like to say base because that b is big because it's the base. Okay. That letter y, I call it the exponent. And it is because it's in the air. Hello. And then that x is the answer. And it is the answer because it's what the equation is equal to. Okay. So the reason I use this instead of byx is it's easier for me to remember. Just watch. Exponentials start with b to the e equals a. B to the e equals a. That's easier for me to remember because I know b is base, e is exponent, a is answer. You can use this b to the y equals x, though. It's okay. And then, so we just covered this one. B to the e equals a equals base, and that is the exponential form. That's why it's underneath this exponential form. Then under logarithmic form, it looks weird. All of a sudden I have a log, and that log means logarithmic, and it means inverse of the exponential, and we have a special button on the calculator for it. Okay, anyway, but this says that we have, mine's written a little bit differently from my handouts, but I'm going to use it just to start with. It says we have log, and then in the basement, in the subscript, there's a number. That's why I call B basement, because it's down under. Okay, and then we put the answer is big and normal, and then it's equal to the exponent, big and normal. And you're saying, now hold up on a minute. Why is the answer swapped around? Because these are inverses. Their information is the same. They just look different. Okay, so let's look at number 1. It says, write each equation in exponential form. Okay, which one is exponential? The one with the log or the exponential? Okay, so we want b to the e equals a. Okay, well, what does that mean they gave us? They gave us a bunch of LOGs. So this looks like log base answer equals exponent. Yeah, where 4 is the base, 16 is the answer, and 2 is our exponent. So I labeled this not according to this hoopla, according to this hoopla. So since it already started with a log, that little number 4 in the basement, we're going to call it the B. Yeah. That big fat 16, we're going to call it the answer. That 2, we're going to call it the exponent. And now we want b to the e equals a. So let's try it. What did we say our b was? 4. What did I say? What did we say our e was? E was an exponent, 2. And this is where it gets kind of rough because we have this e from the word exponent, but then we also had that word, that letter e from compounded continuously. Yeah, okay. But this e means exponent. Okay, so we have 4 to the 2 equals whatever the a was, the answer, which was 16. Okay, 16. Hey, this is the exponential form. And these exponential forms, they should make sense when you read them. The logs might not make sense. We haven't figured those out. But this part we should understand. 4 squared, 16. Ba-boom! Okay, so logs are a different way to write exponentials. And there are special rules for logs, but we're not there yet. Okay, so we use logs because sometimes exponentials get crazy and we need special math to help us out. Okay. All right, let's go to number 2. It starts with a log. Well, I'm going to go ahead and label it log base answer equals n exponent. Log b is the 5. A is the answer, and -1 is the e, the exponent. And I'm kind of weird. Whenever I see the word log, I think about this song from when I was a kid. It was some song, rap song. It said, hey, baby. Anyway, back in the day, bae used to be a thing, like your girlfriend or your boyfriend or your loved one. So See how it says bay, 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 bay? So anytime I see log, I randomly say log, bay, bay. And then I start singing that one song from my youth. Bay, bay, bay. I don't know. Anyway, the point is, anytime you see a log, think bay. Okay, there's my bay. Now I want B. All right, let's whip. That B is still the same 5. Only now it's big and fat. That E is still -1, but it's tiny in the air. A is that big old 0.2. And remember, all of these exponentials you should be able to check in your calculator. 5 to the -1 is 0.2. Yes, again. So I see a log, and I'm going to say, hey, baby. So B-A-E. Okay, now let's rewrite it. B to the E equals A. So B is 8. E is that 0. And A is that big fat 1. And you're thinking, hold up, wait a minute, what? Something to the 0 power can be 1? Heck yes, it can. Remember when we were doing exponential functions and we were graphing? Anything to the 0 power, no matter what witchcraft or sorcery is in the middle, it always pops out a 1. 1. Yeah, okay. So this 8 to the 0 is 1. All right, next thing. Hey, baby. Bia. Yeah. So base is big. 23. E is the exponent. 0. That A is that 1. And again, 23 to the 0 power is 1. Okay. Now we're going to go bass backwards. So before, we started with log baby. And then we went to Bia. Now check it out. It says write each equation in logarithmic form. And it looks like we start with Bia. But it says we end in logarithmic form. That means they want log baby. Yeah. Okay, so let's look at this. 2 to the 4 equals 16. I'm not going to label it baby because my bay comes from if there's a L-O-G on it. So these are not bay. These are Bia because they have an exponent in here. Okay, so let's label it. Me, E, I. Okay, and then now we're going to write it. Log B. B is a subscript. It's in the basement. Tiny little bit. A. Whatever our answer is, it's big and fat. Our A is 16, and it's big and fat. Okay. Did I do that wrong? No, I didn't. Okay, so we got log B, A, and then equals E. What's my E? Oh, 4. Okay. Let me show you how to write that like on lines. We say log, and then see the 2 is in the basement. Then the 16 is big and fat like normal, just like the LOG. And then the 4 is big and fat like normal. So everything is big and fat like normal, except for that tiny little 2. It's in the basement. All right, and that's called a logarithm because it has a log in it. And you might be thinking, I thought you said logs would make things easier. They will. Not yet, though. We're going to have to go through pain. Okay, so let's go to number 6. It starts with a base and an exponent. So it's a Bia. And we want log baby. So we put log B. So our B is 27, and it's in the subscript. So it's tiny, like a little baby. Okay. Then we have BA. A is 3. and E is 1/3. And let me show you how to type these in the calculator to check. If you want to check, you might not have, that's a check mark. That's a check mark. If you want to check to see that you did it right, you might have to use your app on Calc 84, but most of our calculators should be able to handle this. Okay, we're going to press math. Well, first, let me turn it on. Okay, math. Math. Then you're going to press down a ton until you get something that looks like log bay. It looks like capital A, you see it, log base. And all these boxes pop up. And I'm going to type 27 in the bottom box. Then I'm going to arrow out to get the 3. And when I press enter, it better be 1/3. Yeah, 0.333. That's 1/3. Okay, good. Yeah. All right, so that's how you can check to see if you put your stuff in order correctly. All right, again, this is BIA. Only our B is really big. It's a fraction, but don't be scared. So we're going to say log. Then we got to put that B in the basement. So 1/4 is in the basement. A is big and normal. So big and normal A, which is 16. And then what is it? Equals E. So equals big and normal, -2. And if you want to type that in your calculator to try and check yourself, press math down to log base. And in that basement, you can either do just plain old 1 divided by 4. Hey. Or you could put 0.25. Or you could even try and use that alpha y equals enter to try and get some little boxes. I'll just put 1 divided by 4. And then you're going to put 16 in the big box. And it should be equal to -2. Let's see. Okay. So, exponentials and logarithms, they mean the same information. Both of these equations are true. If I were to type this 1/4 caret -2, it should pop out 16. So both of these statements are the exact same thing. They represent the same information. They're just written a little bit differently because we need to learn a new form of math to deal with exponentials. Okay, let's look at this sucker. It says evaluate logarithmic expressions. Okay, there's a way to cheat this and a way to do it in your head. Let me tell you the cheat. The cheat is to do that math down to log base and then type this in. Yeah, okay, so let's try this. Log 12, 144. Math. And I get 2. Let's figure out why we get 2. Where do you think we get 2 from? From 12 and 144. And remember that we're dealing with exponentials. Well, you might remember that 12 squared is 144. Let's see how our calculator did that. Okay, first, our calculator saw that this is log baby. Yeah. And so the B is 12, the A is 144, and the E, well, we just don't know that. It's a question mark, okay? So we are going to now convert to B to the E equals A. And let's see what happens. When I move my business around, that B is now a 12, big and normal. That E, what was it? question mark? Okay, question mark. Equals, where's that A? Oh, 144. Okay, and then from here, this is the part that people don't like. You have to play a guessing game. You have to just use the caret button and start typing numbers in. 12 to the 0? Nope, that's 1. 12 to the 1? Nope, that's 12. 12 to the 2? Oh, hot dog, that's 144. Okay, so this question mark has to be a 2. So when it says evaluate log 12 144, remember we did that earlier, and we got 2, so the answer is just a 2. And the reason it's a 2 is because we looked at the base, 12, and we said, what in the world exponent will pop out that 144? Okay, let's try again. 9. First, we're going to label it log baby. And it looks like the E is question mark. And again, I'm using log bay, because it has a log on it. If there wasn't no log, if there were not a log, I would be using b to the e equals a. Okay, so now let's convert b to e to the e. Okay, let's plug our goodies in. 64 is the b. E is the question mark. Dat A is the ocho. Okay, awkward. Okay, okay. Let's see here. I know that y'all know that 8 squared is 64, but who cares? I mean, that's not what we're looking for here, because we're looking for the question mark on the 64, not the 8. Hey, but we can use this information to go backwards. For example, let's see here. Another way to say 64 can become an 8 is you might be thinking of, I don't know, like square roots. You know? Like if I put a square root on top of that 64, it pops out at 8. Hallelujah. It does. Yeah. And the square root is the 1/2 exponent. So our question mark or our exponent is supposed to be a 1/2. What? Let's check it. I'm gonna say 64 caret 1 divided by 2. Holy hot dog. What? Okay, so even though you knew that 8 squared was 64 and I said who cares, it was actually awesome. Because that squared is where the 1/2 comes from. Let's say if I would have had 64 to the question mark equals 4. What? Well, let's see. 4 squared is 16. What's 4 cubed? Hot dog, 64. So to go backwards, so to go from small to a big number, we have to use a positive exponent. To go from a big to a small number, we have to use a fraction. So this arrow, or this question mark, would be 1/3. Because if I put, oh gosh, I don't know what I'm doing. What am I trying to do? Well, I'll just do it. 64 caret 1 divided by 3. That's like saying the opposite of the cube root. And holy poop, it comes out to be a 4. Yeah. So first, start off with what you were thinking about the squared. But then remember that to go from a bigger to a small number, you might have to use like a square root. And on those tricks from college algebra, on that 4.2, it says something about square root fractions give exponents of blah, 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 blah. Yeah, okay. So if you go from a big number to a little, use a 1, try and use a fraction in the air. Okay, let's look at this last one. Whoa, it gives me a fraction. Uh-oh. Well, let's first label it Bay. Hey, Bay. And the E is question mark. That looks all funky, but you get the point. Okay, now let's convert to B to the E equals A. Well, B is 3. E is question mark. Answer is 1 over 27. What in the world? Okay, well, first we're going to start off normal with just like some squareds in the air. 3 squared is 9. Is that the number I wanted? 9? No, I want 27. Okay, 3 cubed, let's see, 3 times 3 is 9 times 3 should be 27. Hot dog. Okay, so 3 to the 3 is 27. So I definitely have my 27 number. But how does it go underneath a fraction? Well, remember when we were doing exponentials? Negative exponents sent us underneath a fraction. Oh my goodness. Negative exponents sent us underneath a fraction. Okay. And if we look at our tricks from those college algebra handouts, it says negative exponents give fractions. That means you start with a big number and you end up with a fraction. That's when you need to use a negative exponent. So 3 to the third is 27. But 3 to the negative 3? That's supposed to be 1 over 27. Let's check it. 3 up negative 3. Okay, press math, enter, enter. Oh, okay. So this question mark has to be a negative answer. Yeah. All right, let's keep going. The next thing we're going to talk about is the different names of logarithms. First, we have a common and a natural. If we are looking at those tricks from the college algebra, this is what we're talking about. If you see a log with no base, like this is called a common log because it has a pretend 10 underneath. And it's just the LOG button in the calculator. So I already showed you one way to get to a log, and it was this math button. Remember math? Where was it? Math down, log base. Okay, math down, log base. But these buttons are for if you have some funky number down there in the basement, like 27 or 12. Yeah. If you don't have anything in that basement, then it's called a common log, and we just use this simple LOG. And you see how above the LOG, there's a 10? That's because those are inverses. That's how you remember them. Then it says things are called natural logs if they have an E as its base. And natural logs, this is real funky, but the way we write natural logs is not NL. It looks like LN. In your homework, it looks like IN. See how this looks like an I? But you have to use the L button on your keyboard. Or on when I write it down, I usually say capital LN because I don't want it to look like one N. And on your calculator, LN is right here. Okay, so that sucker would look like, LN51. So the 51 would still be there. It would just say LN for natural log, and it means you have a little E down there. And that little E means Euler, and it's probably involved in some natural word problem about plutonium or flowers or the population of Mexico or something like that. Okay. All right, so common logs, if you look, they are missing that basement number, that b, and we pretend it's a 10. Then natural logs, they're written as ln, and here they have it two different ways. You can either have y equals log ex or y equals ln ex. Those are both the same, and they will yield the same answers. That means they'll give you the same answers. All right, let's keep going. So far, all we've learned is how to flip-flop, swap between something that looks like an exponential with an exponent in the air, something that looks like a log with a log, and then we kind of like used our brain to try and answer what a log would be. We tried to figure out what it was equal to using our brain. All right, I'll keep going. This one says, evaluate each expression. Well, heck fire, where are all the basements? Okay, so these first two suckers, they have log. Those are called common logs. And they have a 10 in the basement. So let's slap little 10s down there. Hey. Okay, now these other two suckers, they have a ln. So that's the natural logs. Did I spell it right? And those have an e. So let's put a tiny little e. All right. Now it says evaluate. That's the same thing we just did, where you put like a question mark, label it bay, convert it, figure out that question mark. All right, let's go. I said label, what did I say? Oh, put a question mark. Label it bay. Hey, baby. Hey, baby. Hey, baby. It sounds like hey, boo boo. It's like a cartoon. Anyway. Okay, so we got bay. Okay. And on all of these, we want b to the e equals a, and then the question mark. That's what the whole point is. Okay, so let's rewrite this as b to the e equals a. We're going to have b, 10 to the e, question mark, equals a. A. 100. Oh, and then you figure out the question mark. Well, what do you think the question mark is? 2, correct, because 10 to the 2 gives you 100. All right, let's try it again. Let's go to this second one. It looks awkward because of the decimales, but we're not going to freak out. All right, we're going to have 10 to the, so B, because we're doing BIA. So I got the B, 10. The E is the question mark. Dat A is the 0.0001. Yeah. Okay. Now, let me show you let me show you a rule of tens. Okay, so let's say we're talking about exponents. We have 10 to the 1. That means we just have 10. And another way to say that is 1, 0. See how there's 1, 0 right there? Okay, 10 squared. That's 100. That's 2 zeros. Do you see what's happening? Yay. So 10 to the 8 would be 8 zeros. You see what's happening? Yeah. But it wouldn't be 8 zeros after the number 10 because this 100 is 2 zeros after the number 1. So, okay. That means that my 10 to the 8 is going to be a 1 with 8 zeros. Hey, yeah. Okay, let's go backwards. How about 10 to the negative 1? Well, that makes 1 over 10 to the 1, or 1 over 10. And what's 1/10? 0.10. Okay, let's go again, see if you can see the pattern. 10 to the negative 2 is 1 over 10 squared, or 100, or point. Hold on. Okay. Let me rewrite that 0.1 a little different way. Okay, this 10 to the negative 1, I'm going to label it 0.1, or 0.1. Okay, then this 10 to the 2, it's 0.01. 10 to the negative 3, 0.001. Okay, so let's see here. The amount of zeros has to do with the exponent. So over here on the left, when we had positive whole numbers, you say 1, 2, 8 zeros after, or let's say to the right of 1. Yeah. But for negative exponents, you say 1 0, 2 zeros, 8 to the left of 1. So if you have whole number positive exponents, it makes the number of zeros go to the right of the number of 1. If you have negative exponents, it makes your zeros go to the left of 1. Okay, so the whole point of that was because, where? Right here, this 0.001. Now, let me make sure I put the 0 in front of my decimals so that I do this right. So let's say 10 to the question mark equals 0.0001. There we go. Okay. So we have to say, what question mark will give me this? Well, we kind of already talked about it. 10 to the negative 3 means you have the number 1 and then 3 zeros before it. And remember, one of those zeros starts off your decimal. Okay, well, if we have 10 to the 4, we're going to have 1 with 4 zeros to the left. And that's what we have, 1, 2, 3, 4. So that means this exponent has to be a negative 4. Or, if you didn't remember all this, you can just play the guessing game and say, oh, okay, 10 caret 2. Oh, my bad. 10 caret 3 is, 10 caret 4 is, we're getting too big, so let's go low. Let's maybe use negative numbers. 10 to the negative 1. 10 to the negative 2. Okay. Yeah, you get the point. All right, let's look at 13. 13, we already labeled it bay. Let's rewrite it bia. When we rewrite it bia, it's a little confusing because we already have a ton of A's and E's on this paper. But it's okay. Let's do it. Okay, so B to the E equals A. What did I label as the base, as the basement, as the subscript? A pretend E. You see how the pretend E is the subscript, it's the basement. And we know it's a pretend E because LNs have pretend E's. Okay, so our basement or a subscript was a pretend E. Okay. Now what we have to put in the air is, what does this E stand for? Exponent. Okay, yeah, so I have to put whatever the exponent needs to be, which is question mark. Just like it has been for the last two examples. Question mark, okay? And then it's equal to the answer. So what did we label as the answer? Our big fat A was this e to the negative 3. And then this is a silly question. What do you have to put in that question mark so that the left looks like the right? Negative 3 goes where that question mark is. Yee. Okay. Let's look at 14. We already labeled it bay. Now we label it bia. Base, or the basement. What was our basement? It did not have it, but it has a pretend e. Okay. What needs to be our exponent? Well, let's label what I labeled e, or let's find what I labeled e. Nope, that's not it. Nope, that's not it. This is it. Question mark. Equals, what did I label big A? E to the 10. All right, so what do I have to put? This is a 10. What do I have to put on that left side where that question mark is so that the left looks like the right? The 10. Okay, awesome. All right, next. So we've gone over logs with basements of whole numbers, positive. We've gone over logs with no basements, so we put a pretend 10 down there. We've gone over LNs with pretend e's in the basement. Okay, let's see what we're doing next. It says use your calculator to find the approximate value, round to 4 places, check your answers. Okay, this is just, they show you how to rewrite it, but you can also put it in your calculator. So if I wanted to do this the rewriting way, I could say, hey, log baby, hey baby. And I could say, oh, this log is naked. He needs a 10 down there. Okay, because naked logs have 10s. Then let's rewrite it as b to the e equals a. So b is that 10, that pretend 10. A is the 4 to 3. That's like, just like y over here or something. Okay, and then e is that 1.6335. Okay, what we're going to do is we're just going to type it in the calculator. Okay, since this has no basement, we're just going to use regular log. What about this guy? Regular log. Good. What about these last two? ln. If it would have said log 1381, we would use math down to log base. Kind of like we were playing around with on number 6 on the front of the page. Remember, we were just kind of playing around. Yeah. Okay. All right, so in our calculator for 17, we're just going to type, hey, log 200. And we're going to round it to 4 decimal places. So that means I need 5 to the right of the decimal. So 2.30102. That's 5 decimal places. Now let's round it to 4. That 2 is 4 or less, so we're going to let it rest. And that 2.3010, you could probably just put 2.301. Hey, we just evaluated it. Or we used our calculator to find the approximate value. Okay, let's look at 16. Again, log. And if we forget to put the first 0, it's still cool. We're okay. See how I forgot to put the first 0? It's cool. And I'm not closing my parentheses. That's cool too. Who cares? All right, so this gets negative 1.1376. Yeah. Okay, and I want to round to 4 spots. So let me... Okay. And this 6 is in the 5th, and 5 or more, you up the score. So this is going to go from negative 1.1307 to 0.8. Yes. Okay. Now let's look at these next one. Ln. We get 5.2983. What's another one? What? And you might be thinking, what the heck? How is this answer different from 15? Well, remember, number 15 truly represents log little 10, big 200. That's what 15 represents. 17 represents ln with an e in the base. And remember, e is like 2.71. Anyway, and remember earlier on the last page, I said, hey, you can either write it as ln E200 or log E200. So the reason that these two problems have different answers is that the 15 has a pretend 10 as its base. 17 has a pretend E, or E is like the number 2.71. Or is it 2.17? I can't remember. Anyway, pretty close. So I just did ln200. Yeah. Okay. I wrote down 5 after the decimal. Let's round to the 4th. So we're going to have 5.298 what? This 1 is 4 or less, so we're going to let it rest at 83. Let's look at ln 1. We get 0.0049, one more, 8. And if I want to round that to the 4th spot, there are my 4 spots. The 5th is an 8, that's 5 or more, up the score. So I'm going to round this 49 to a 50. And if you want to, you don't even have to put the 50. You can just put the 5. You don't have to put that last 0. All right. The next thing that we need to go over is something that we kind of already figured out. We already figured out that anything to the 0 power is 1. Like 2 to the 0, 4 to the 0. That's what I mean. Okay, so anything to the 0 power is 1. And its matching piece of information for logs is if you have log of 1, it's equal to 0. Who cares what's that b is? That b could be any number around the world. But as long as it says log with a 1, it's equal to 0. So let's see if I have any log 1s. No. Oh, yeah. Yeah. Who cares how big that 273 is? The point is this 1. So every time we have log of a big fat 1, it should be equal to 0. And if you don't remember why, it's because if we say, hey, baby, where the E is a question mark, and we rewrite it to BIA, we get 273 to the question mark equals 1. What's the only thing that I can put in that error to give me a 1? 0. Yeah. So that's why that question mark has to be 0. Okay, do we have any other places of a log 1? Oh, here it is. Who cares that that 1/8 is 1/8? The fact that we have that 1 is the important thing. Who cares what that 1/8 is? Okay, log 1. Okay, let's look at another trick. This trick says, if you have log, and then look at that. It looks like the basement and the big fat number are the same. Okay, and anytime that happens, if you have the same little number and big number, it equals whatever your exponent is. So since this exponent is x, it's equal to x. So if you have the same numbers, it's equal to the exponent. Right? So let's look for the same numbers. Here I see a same base and big number. Here's one too. There's a couple others, but let's just start with those. Okay, so for 19, I see the same two numbers, the basement and that big number. So that means the answer is its exponent. Well, what is this exponent up here? That's 19 to the 1. That's a 1 exponent. If something doesn't have an exponent, you put a 1 on it. Yeah. Okay, let's look at 24. We have the same basement, or the subscript, and the same big number, 30. So the answer is its exponent. Hey. Okay, let's look for another sucker. Oh, this log 1919, I think it's actually this one also. I forgot to go over that one. Yeah. See how the numbers are the same, same. It equals 1. The only thing is on this equation, there's no exponent. So this is like number 19. Since there's no exponent, we put a pretend 1, and that's why it's equal to 1. Okay, let's look at 20. We got a couple of issues here. First, we're missing that subscript. Well, it's either a pretend 10 or an E. It's a 10 here. Okay, so now that we have a 10 down there, it looks like this equation, where it says if you don't have an exponent, it's a pretend 1. And the problem is equal to, or the answer is your exponent. So log 10 should be 1. And you could put this in the calculator, but I'm just showing you how to do it in your head. Okay, for this LNE, what's underneath? A pretend E. What? And then since these two suckers are the same, the answer is whatever the exponent is. Well, what is our exponent on this big fat E right here? I can't see anything. The one that's already typed. It has a pretend 1. Yeah. Okay, let's look at this sucker, 25. It has a pretend E in it. And then, when we have the same big and little, like basement and big number, the exponent is your answer. So the answer to this one is -12. Okay, let's look at these last two. Looks a little funky. They look like, where's it at? I think it's this one. Yeah. This one says, you can barely see, but I think it says B, and then log B. You see how those are the same? The big number, and then the little bitty basement number. Yeah. And then it's equal to whatever is after that log. That's what we're going to do here. So that's an example of this. And first, I see my big number 10, but I'm supposed to have that same number in the basement. So I'm supposed to have a B in the front and a B in the basement. Okay, well, I got that 10 in the front. And what's in the basement? A little baby 10? Yeah, because logs with no basements have a 10. And then it's equal to whatever comes after that, 14. Woo! Let's look at 27. It's the same thing. We have 8 and then 8 in the subscript. So those cancel out and we just get what's after that 8 log 8, which is the 5. Okay, so basically the point of that was if you see a tiny number and the big number, and they're the same, it cancels out to the exponent. So this tiny number, big number, cancels out to the exponent, 1. Here, tiny number 8, big number 8, cancels out to the exponent. What the heck is left in the air? Cinco, 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 cinco. That's where the cinco comes from. Okay, let's keep going. Okay, the graphs of logs, we're not going to go too hard on them. We're going to probably use decimals and stuff, but the graphs of logs are inverses of exponentials. So if you remember, exponential growth, I think, was like that, with that asymptote going side to side. Yeah. Okay, the inverse of this puppy, remember, we flop it over that diagonal line. And the inverse actually turns out like that, with his new asymptote being up and down. Okay, so logarithms and exponentials, their curves look the same. They're just flopped over that crooked y equals x line. And their asymptotes are different. Okay, for exponential growth, the asymptote was, what was it? Y equals 0. Or like the really big fat number. Yeah. But for logarithms, and we don't have growth or decay for logarithms, so don't worry about that. But for logarithms, it would be x equals 0, or the big number. Crap, hold on. I forgot. Yeah, or, yeah, and the big number being added or subtracted to your x's. Yeah, okay. So, usually our asymptote is 0. X equals 0. It goes through the x line. See how this side-to-side line is x? The asymptote goes through that x line, so it's usually x equals 0. Unless you have something being added or subtracted to your x's. Well, let's look at 28. What do I have with my x? Nothing. It's like plus 0. So this asymptote is still going to be at x equals 0. I wrote that kind of weird, but whatever. Okay, let's look at the one below. Oh, we're adding a 1 to our x. So that's probably going to be my asymptote. Yeah. And unfortunately, the way these asymptotes work, when they're inside here, it's opposite of what you think. So if we look down here at the transformations, earlier when we were talking about exponentials, we saw that if you have a big fat number added out to the side, it moves us up or down, as in this k right here. If I have a number added out to the side, it moves us up or down. But if I have a number inside, it moves us left or right. Okay, and it says x minus h. So we have to make it look like that form with the x first and then the number. So this says 1 plus x. This is the same as x plus 1. Yeah. Okay. And then it says if h is bigger than 0. Okay, here's the thing. If h is bigger than 0, you might be thinking, oh, this h is +1 because it says a +1. No. Look at this formula. It says minus. So I want to know x minus what gives you this +1. So what do I have to put in this little box so that it will pop out a +1? So right now, if I just put a 1, it looks like x minus 1. This would be x minus 1. That would be a h bigger to the 0, and I would shift to the right. But these two aren't the same. To get this +1, I have to put an extra -1. What? Yeah. So 1 plus x is the same thing as x plus 1, because the 1 is positive. But then to get that 1, it comes from a double negative, where that -1 that we just found is h, and h is less than 0, so go to the left. See how it says h is less than 0, go to the left? Yeah. So that means my asymptote is going to go 1 to the left. So instead of x equals 0, right up in the middle, we're going to shift it over left. We're going to go left 1. So our x is equal to -1. Okay, earlier I said some hoopla about opposite. Yeah. Instead of doing all of this and thinking this way, where you have to turn it to make it look like x plus, then you have to make it look like a x minus something so it matches the formula. Instead of all this hoopla, just think opposite of +1 is -1. And that's where I got my asymptote. So instead of following all this rigmarole and all this hoopla up here, if you didn't understand that, just know that if you have something in the parentheses, your asymptote with that x, your asymptote is opposite. So not x equals 1, x equals -1. Okay. Is there another one? Nope. Okay. All right. Now we're going to graph this. And usually when we graph it, we pick, I think we usually pick like a -2, -1, 0, 1, 2, something like that. Yeah, okay. But unfortunately, not all these are going to give me beautiful y values, but we can try them. Let's try. -2, -1, 0, 1, 2. I think I left off some. Let me try maybe a -3 and a 3. Okay. All right, in my y equals, I'm going to go to y equals. Then I'm going to type in math. I'm going to press the math button down to log base. And then I'm going to type my goodies in to make it look like y equals log 3x. Okay, so I'm going to go to y equals math. If you can't get that log base off your own calculator, it's because it's too old. So you need to get the app and download that. Okay, so I've typed in log 3x. Then let's go to second graph. And you can see that at -2 we have error. -1, error. 0 error. 1 is 0, 2 is 0.6, we'll just kind of guess. -3, oh, that was error. 3 is 1. All right, so error, that means that part of the graph does not exist there. So if I go to my picture graph, you can see, nope, you can't. You can see that when x, because the x-axis goes side to side, and at -1 and -2, here's -1 and -2, there ain't no graph over here. Yeah, that's why it says error. Okay. So let's graph what we can. 1, 0, and see how the x's are being counted by 3's. Be careful. 1 is not all the way to this 3. 1 is like, yeah, okay. Then the next one we have, the good point is 3, 1. Oh, 2.6. Okay, 2. And then maybe I can look at my T-chart for some more. What other good, like, whole fat numbers do we got? I want some whole fat numbers. 9, 2. 9, 2. Let's look for some whole fat numbers. Where are my fatties at? Let's see. 3. 27, 3. 27, 1, 21. Okay. And then I'm missing something, I think. Okay. And then I told you logarithms look like, and then they fall straight down. So let's go straight down. Okay. Hey. And then my asymptote should be at x equals 0. And remember, for exponentials, the asymptotes went side to side. Logarithms are up and down. And it's at x equals 0. So right up on that y-axis. Okay, for the next sucker, we're going to do the same thing. We could do this by hand, but we're going to put it in the calculator because I've already taken too long. Log base 2. Whoops. I don't think this will not make a difference, but let me just rearrange it. Okay. First, let me look at my picture. It looks like it kind of sifted over. Let's go to our T-chart and see what we got. Usually we go from -3. Oh, okay. Well, -3 is error, error, error. 0 is 2. 1 is 3. 2 is 3.6. 3 is 4. All right, let's draw these. Okay, and remember, logs come and then they fall straight down. But I just need to figure out where they fall straight down. I need to know where my asymptote is. My asymptote is at -1. So when I fall straight down, I'm just going to hover along that asymptote all the way down. Okay. The next just tells you the general differences between exponential and logarithms. Yeah. And let's remember that exponential, whoops, oh, I messed that up real bad, is this top curve, and then logarithm is this bottom curve. Okay, let's look. If you check out their domain and range, they're bass-backwards of each other. The domain of the exponential is the range of the log. And that makes sense because they're inverses. And when you do inverses, you swap the x and the y. Then if you look at the domain and range, again, they're equal to each other. So the domain of one is the range of the other and vice versa. Okay? Our asymptote comes from, on our exponentials, my asymptote comes from my range. On logarithms, my asymptote comes from the domain. Whoa. Okay, and then they pass through similar points, 0, 1, 1, 0. Okay, 30 says, give the domain and range in interval notation, write an equation of the vertical asymptotes. Okay, so vertical asymptotes for logarithms, they come from the domain. And remember, the domain or the vertical asymptotes come from the big fat number that's being added or subtracted to the x. All right? Okay, so it says, give the domain. Okay, let's go. Domain. For logarithms are something to infinity. Okay, or range is always negative to positive. It says find the asymptote. What's our asymptote? It's x equals whatever the number is from your domain or the big number that's being added or subtracted to your x's. So our asymptote is x equals, hey, we would say 3, but let's remember. Remember on that last page, our asymptotes from the logs don't come from directly from the number inside the parentheses. It's the opposite. So if I see a positive 1 in the parentheses, the asymptote is a negative 1. So I see a positive plus 3. So the opposite is negative 3. So my asymptote is x equals negative 3. All right, let's look at this. If I have my asymptote at negative 3, what's my domain? It's from negative 3 over to the right. And we have a parentheses because of that asymptote. Yeah, it means we can never touch this asymptote. Okay, let's look at this sucker over here. First, we got to look for if we have a number added or subtracted with the x. We don't. Dag darn it. Okay, so let's go ahead and do our domain, our range, our asymptote. Okay, our asymptote is the opposite of whatever we're adding or subtracting. Well, the opposite of 0 is still 0. So our asymptote is 0. Okay, remember that whatever our asymptote is, that's how we start off our domain. Okay, so our domain is parentheses 0 to, starts at 0, goes all the way to infinity. Okay, let's do range. Range is always negative to positive infinity. All right, let's look at the, oh, what is this? Okay, so first, we got to figure out the opposite of what's inside these parentheses. But to figure out what's opposite, they have to look like the form x plus something, x minus something, or x plus something, x plus something. As in, we need to factor this. Dag darn it. All right. Well, if I factor it, it has to add to negative 3 and multiply to negative 4. Okay, and we break up the negative 4. What numbers multiply to negative 4? 2 and 2, but will that ever add up to a 3? No. Okay, so how about 4 and 1? All right. And to multiply up to a negative 4, we either have to be negative 4 positive 1 or positive 4 negative 1. Which one of these is going to add to negative 3? This one. Okay, so this is the same thing as x minus 4, x plus 1. And remember, now we needed to take the opposite. So the opposite of -4 and +1 is +4 and -1. So my asymptote should be x equals 4. And it doesn't look like this is x equals 4, but I'm thinking these are counting by something. Let's see. I think these are counting by 2. Yeah. Okay, so there's x equals 4. And then x equals -1 is right here. So we have 2 asymptotes. All right, let's do our domain. Our domain is a little different, okay? We definitely have that 4 to infinity to match with this asymptote of x equals 4. Yeah. But now we need to describe this left-hand side. Well, it looks like this left-hand side goes from way over here on the left all the way up to this asymptote of -1. So it looks like this left part of the graph covers negative infinity all the way to the x value of -1. So we're going to put u negative infinity all the way to the x value of -1. All parentheses because these are asymptotes. Range, same as always. Yay! Okay, crazy word problem. This is the word problems that actual, like, real life mathematicians and, scientists and stuff use. All right, it says the absolute magnitude, m, of a star is the apparent magnitude, m, a star would have if it were placed 10 parsecs from Earth. We don't know what that is. It's okay. The lower the value of the magnitude, the brighter the star. Our sun has an apparent magnitude of -26.74. The brightest star in our night sky is Sirius, the dog star, with an apparent magnitude of -1.44. The sun appears so bright because it is very close, astronomically speaking. The formula relates a star's absolute magnitude. So I think capital M means magnitude. Apparent magnitude, that's the little m. And its distance, d, from Earth in parsecs. Parsecs are kind of like miles or kilometers, only it's such a big distance. There's a new unit, and this is it. Okay, it says if Sirius is 2.637 parsecs from Earth and the sun, what is the absolute value? Okay, so it says, what is the absolute? So that means capital M is question mark. Okay. And then it says something about 2.637 and then this other number, but it doesn't say the word apparent. We need to figure out which one is apparent. Okay. It says our sun has an apparent magnitude of -26, and then it says another one of -1.44. So there's 2 little m's. So the m for the sun is -26 point, and then the star m is -1.44. And you're probably wondering, why did they give us 2 different lowercase letters? Well, let's see. It says, what is the absolute magnitude of each star? So we want to know the capital M for the sun, because the sun is considered a star, and for the dog, or what's it called, Sirius. So that's why they gave us 2 pieces of information in the question, because first we got to do our business for the sun and then for Sirius. Okay, so if we know our little m's, the only thing we don't know is the d, distance from Earth in parsecs. And that makes sense now. If Sirius is 2.3 parsecs, okay, so that's the d of the Sirius, and the d of the sun is this awkward exponential notation. Okay, Let's use our formula. Okay, so we're going to have capital M equals, we're doing the sun first. So the sun has a little m, not of this 10 to the negative 6 thing, as of a negative 26.74 minus 5 log parentheses. What's our D? Our D for the sun is this 4.8 over 10. Okay, well, first we got to remember some old school. We could probably put this in our calculator if you want. Let's see if we can. And then I'll show you why it happened. Oops, so just in your blank screen. What am I doing? And this log does not have a subscript, so I'm just going to use the regular old log button. And then I think I'm going to go ahead and press my alpha y equals enter to get this nasty stuff. All right, now on the top, 4.8810 times 10 caret negative 6. Down below, 10, out to the side parentheses. Okay, it looks like we have 4.8. Okay, let's see if we get that same answer using math, like actual math. Okay, first off, one thing that you might have forgotten from when you were a kid is this 10 has a 10 to the 1. And when we divide tens, or when we divide the same bases, see how I have a big fat 10, big fat 10? We have to minus the exponents, as in top minus the bottom. As in negative 6 minus 1 equals negative 7. So this becomes negative 26.74 minus 5 log okay. And then let's check it this time. Maybe it'll be a little bit different. Or if it's the same, we can go ahead and write it as our answer. Oh my goodness. Oh gosh, I don't know what happened. Hold on. Yep, okay. So, the absolute magnitude of the sun is, it didn't tell us what to round to. I'm just going to say 4.8 parsecs. Magnitude is like a distance. And since our distance to the sun was parsecs, this is parsecs. Okay, now let's do the same thing but with Sirius. So we're going to have m equals Sirius's little m, which was right here, negative 1.44, because it says Sirius, the dog star, paramagnetic. Okay. So negative 1.44 minus 5 log. And then Sirius is just 2.637 over, and then we divide it by 10 still. All right, let's throw it in. Okay, I got, let me try one thing just to make sure it doesn't change anything. No. Okay, yeah. In this one, I got 1 point, I don't know, 5-ish. You'll have to check your homework what they want you to round to. Parsecs. And then, oh, that's it. Okay, yay, done with logarithm. Well, one section.